Hey, so in the previous video you watched that I assigned, we learned about this thing called solubility product, and what we're going to do here is we're going to actually solve a couple problems using solubility product. So as mentioned, if I have something, so this question says KSP of magnesium fluoride is 8 times 10 to the minus 8. And then this is asking how many grams of magnesium fluoride will dissolve in 0.25 liters of water. So, as mentioned, we have MgF2. And if I want to write the dissociation for that, then that is like this. Remember, it's slightly soluble, so it's going to split up into my two ions, Mg. And from that, we have 2 plus charge. And then F is a negative charge, but we have 2 of them, so we have a 2F here. Okay. And if I write the KSP expression, well, the KSP, remember, is concentration. So the products over reactants, but we don't write the reactants in the KSP expression because this is a solid. So Mg2 plus times F negative, and that's 2 of them, so it's squared. So that's my KSP. That's equal to 8 times 10 to the minus 8. Well, I want to figure out how many grams are going to dissolve in it. And to figure out the grams, I first need to get the moles. Or this thing called molar solubility. And that tells me how many moles of that substance will dissolve in 1 liter of water. Okay, so we go ahead and start this off. Remember, I don't worry about this at all. I'm gonna have, it's not in any particular solution, so I don't have magnesium ions, extra magnesium ions, or extra fluoride ions that I'm dealing with. It's water and not like magnesium nitrate, or so I have zeros here. We'll have the cases where we don't have zeros here later. And then remember, this is gonna be plus S. I use S for molar solubility, so S, remember, is this molar solubility. It tells me the number of moles of solute, which is this thing here, the thing that's dissolving, that dissolve in 1 liter of water or solution. Okay. And some people use X here, some people use S. I use S just to, I don't know, I like S because solubility. This, remember, is 2S. And so this is going to end up being S, 2S down here. And if I take this and plug them into here, this S is Mg2 plus. The 2S, because this coefficient is here, it seems a little funky, but 2S is actually the F negative ion concentration. So it's not 2F, it's just the concentration of F minus is going to be 2S. So when I plug this back into here, this is going to be S times 2S squared, which is S times, this whole thing squared is 4S squared, so 2S times 2S is 4S squared. And so that's going to give me 4S cubed, which is equal to 8 times 10 to the minus 8. Okay, so the biggest trick is making sure that you know that whatever coefficient is here, that is just going to be plugged into this concentration of whatever ion that is. So 2S is concentration of F minus. Now, to solve for this, I gotta do some algebra. So it does divide both sides by 4. Okay. So in my calculator, I'm gonna take 8. So here, let's do this. My function, and then I go 8 e minus 8 divided by 4. Okay, so that's 2 times 10 to the minus 8 equals s cubed. And if I want to get this to the cube root, so a couple ways of doing cube root. You can use the math button, okay, and there's a cube root function there. So you click math, click that, and hit answer. That'll give you that answer there. So S, which is my molar solubility, that tells me how many moles of the solid will dissolve in a liter of water. So 0.00271 moles per liter. Okay, that's one way of doing cube root. The other way of doing cube root is if I have some number here and I want to take the cube root of that, it's also, you can raise it to the 1/3 power. So if I take 2 times 10 to the minus 8 and raise it to the 1/3 power, so if I did this, 2 times 10 to the minus 8 raised to the 1/3 power, gives me the same thing, okay? So a couple ways of doing cube root, or however else on your calculator, this is how I know I use 84. Well, still haven't answered this question yet. I still will need to get the grams. Well, remember, and I need to get in 0.25 liters of water. So I'm gonna need some more space on my paper here. I'm gonna go ahead and move down to this spot. So just ignore this question. But if I take this number here now, 0.00271 moles of MgF2 in 1 liter, well, how many is it in 0.25 liters? I can set up a proportion, or I could just multiply it out. But if I set up a proportion, take this, cross multiply, divide, and take 0.25. So that gives me 6.7086 times 10 to the minus 4 moles. Okay, that's how many moles in that many liters. How do I go to grams? My molar mass is 62.30 grams per mole. So I'm gonna take it, multiply by 62.30 grams in 1 mole. That's all right, 1 mole. 62.30, and that gives me 0.0423 grams of MgF2. Okay, so the biggest thing is making sure you know how to get S, molar solubility, and then from there, once you know that, then you can do a bunch of stuff with that number. The next problem on here is calcium phosphate. So it says solid calcium phosphate, add to water, stir for a period of time until equilibrium is established. And then after several days, you still have solid calcium phosphate in the bottom of the container, which means there's still an equilibrium. So it's, something's dissolved out. And the concentration of the calcium ion is 3.42 times 10 to the minus 7th. Now it says calculate the KSP for this. So this problem, they give you a concentration and they want you to get KSP. There are 2 ways of doing this problem. So, they're essentially the same thing, but a couple slightly different methods. If I know calcium concentration. So I know that Ca 2 plus is equal to 3.42 times 10 to the minus 7 molar. And I know this is my equilibrium. Well, how is this related to this? It's a 2 to 3 ratio. Okay, so 2 of these for every 3 of these. So if you know your stoichiometry, and you can say, well, 3.42 times 10 to the minus 7th moles of Ca2 plus per liter. Well, I'm just going to use molar. And I know that for every 3 moles of Ca2 plus, there's 2 moles of PO4. And I go ahead and solve for that. 2.42 minus 7 times 2 divided by 3. That gives me 2.28 times 10 to the minus 7 molar. Okay, so if I know this number, and I know this number, and I now plug it into KSP, so KSP is Ca2 plus cubed, PO4 3 minus squared, right? And so I can take this, plug it in. So 3.42 times 10 to the minus 7 cubed, 2.28 times 10 to the minus 7 squared. This is going to be a really small number. So in my calculator, how I type that in is 3.42 minus 7 cubed. Oops. Let's try that again. 3.42 times 10 minus 7 cubed times, there we go, 2.28 e minus 7 squared. And that ends up being 2.08 times 10 to the minus 33. Okay. I just had to push the right arrow button to get away from that cube. If I want to do this using the solubility, the molar solubility, the way we did before, we can also do that. If you feel more comfortable with that, let me show you how to do that. So I set this up here like this, and I set up my chart so I know that 3s, 2s, bring those down. And I know, this is my, so here, before I do this. Remember, 3s right here, that is equal to concentration of Ca2 plus, right? So 3s is equal to that. So if I wanted to solve for s would just be this number divided by 3. So I know this number here from my problem statement is 3.42 times 10 to the minus 7, and then I divide both sides by 3, right? Divide by 3, and I can get s to be equal to something, okay? So if I did that and I went through all this stuff here, so if I went through the KSP, I solved for 3s is this, 2s is this. I did all my math, cube these, square this. I end up with 108 s to the 5th is my KSP. And if I solve for s using my method above, I did it already. I did it down here. So I took this s, is 1.14 times 10 to the minus 7, and I plug it into here. That's going to give me the same answer. So whatever method you prefer, that you like better, they're the same. Just whatever you feel more comfortable with, they should give you the same answer.